Buenas tardes a todos. Muchas gracias por venir hoy. Hoy vamos a escuchar a uno de los grandes científicos que han ayudado a que la cosmología avance de una forma espectacular, desde luego desde la última década. El profesor David Spergel, con nosotros esta tarde, es uno de los científicos mejor valorados tanto en su país, en Estados Unidos, como en el resto del mundo, por haber hecho este avance posible, el haber hecho de la cosmología una ciencia, si no exacta, al menos más precisa que antes. Es responsable de uno de los experimentos, el Wilkinson Microwave Anistropy Probe, un satélite del que hablará extendidamente en su charla, que nos ha permitido comprender hasta unos niveles insospechados no solamente en qué universo vivimos, cuál es la edad de este universo, sino cuál es la composición de este universo. Está compuesto por la misma materia de la cual nosotros estamos compuestos. Se expande al ritmo que creíamos se expande, y aquí vamos a encontrar sorpresas. En general, David, que ha sido responsable de la descripción científica de los experimentos, de los resultados que ese satélite ha mostrado, es un científico teórico, un astrofísico teórico, formado en las mejores universidades americanas. Se licenció por Princeton en el año 82, hizo el doctorado en Harvard, otra de las grandes universidades americanas, en el año 85, y desde el 87 forma parte del faculty de Princeton, de la Universidad de Princeton. Es, sin duda, como decía antes, uno de los grandes científicos americanos. Tiene un número muy amplio de premios. Es además uno de los cosmólogos con una perspectiva más amplia, y lo hemos tenido la suerte esta mañana de poder conversar sobre ello, y las ambiciones de poder entender en qué consiste ese universo, las perspectivas, que yo creo que es necesario en este campo de nuevos descubrimientos, y que sin duda dará mucho más que lo que ha dado hasta ahora. Pero sin necesidad de extenderme en ello, creo que su charla dará pie a grandes interrogantes, y es posible que algunos de esos interrogantes seamos capaces de responderlo con futuros experimentos, futuras observaciones de ese universo. Sin más, paso la palabra al profesor David Spergel. Muchas gracias por estar aquí.
So let me begin by apologizing that my Spanish is not good enough to lecture. It is good enough to get food in a restaurant and get directions, but I do not trust my Spanish as able to convey cosmology in Spanish. Fortunately, there is a wonderful translator, and I hope those of you who are not comfortable with my English, please use your headphones. I think you'll find they work very well. So what I want to talk to you about today is the remarkable progress we have made in cosmology in the past 20 years, and how we've been able to construct a simple model that fits really all of the astronomical data we have about the early universe. And while this model is simple, is also very strange. And the story I'll tell today is of a strange universe, one in which atoms make up only 5% of the universe, and the remaining 95% of the universe is mysterious. In order to begin this journey, I first have to teach you a little relativity, and then a little general relativity. First, a little relativity. The important idea that you need to have from relativity is light doesn't travel at an infinite speed. Light travels, well, at the speed of light. It takes about a few billionths of a second for light to get from me to you. So you're not seeing me as I am at this instant. You see me as I was a billionth or so of a second ago. The further you look out, the further out back you look in time. It takes light 8 minutes to travel from the sun to us. So we see the sun as it was 8 minutes ago, not as it is today. It takes light 30 minutes to get to Jupiter. This is quite important when you communicate with a probe out at the orbit of Jupiter. It takes 30 minutes to send a signal to the probe saying, please move to your left and look at this satellite. And takes 30 minutes more for the probe to send a response back telling you, yes, I've got your signal, I've moved. Those of you who remember phones that had a delay, it used to be in the old days when we had phone calls between the United States and Spain, there'd always be a delay on the line. And you'd call, and you'd actually have to wait a little bit to get the response. And that's what it's like communicating with Jupiter, except for it's a 30-minute delay. The further out you go in space, the further back you go in time. When you look at a typical star in the night sky, it may be 10 or 20 light years away. If you stood on a planet orbiting a star 20 light years away, you would see the Earth not as it is today, but as it was 20 years ago. So if you stood on that planet with a very good telescope, you would see that I had a full head of hair. The further back you go out in space, the further back you go in time. The Andromeda galaxy is about 1 million light years away, so we see it as it was 1 million years ago. When we look with the Hubble telescope at a distant galaxy, it may be 10 billion light years away, so we see it as it was 10 billion years ago. This is very important for the story I'm going to tell tonight, because we're going to look out in space back 13.7 billion years ago, back to when the universe was only 380,000 years old, and basically take the universe's baby picture. And by looking at out in space at the very early universe, we're going to be able to construct a picture for how the universe forms and evolves. And to talk about the early universe, we're going to have to talk about general relativity and the Big Bang Theory. Some of you may be familiar with the Big Bang Theory from the TV series about some graduate students at Caltech. I don't know if this has made it here, but it's a very humorous show. I'm not going to be talking about the TV show. I'm going to be talking about the theory of the Big Bang based on general relativity. And this picture here, which we'll come back to, represents the evolution of our universe in time, going from the first moments of the Big Bang out to today, 13 billion years after the Big Bang. The Earth formed about here. Advanced life with multicellular life emerged around here. And there's our satellite looking out in space, observing the early universe. As I mentioned, I'm now going to need to train you all to be experts in general relativity. But don't worry, general relativity consists of basically only 2 ideas. The first idea is that matter tells space how to curve, matter and energy. So you should think about the space around the sun like a fabric that's distorted by the sun. The second idea is the curvature of space tells matter how to move. So the Earth is trying to move on a straight line. But since the sun is curved space, the Earth moves in this curved space in the orbit around the sun. And that's how general relativity teaches us to think about matter, space, curvature. General relativity in many ways is very simple. It's just those two ideas. What is confusing about general relativity, I think, to all of us, is that we all tend to grow up with, I would call, a Galilean notion of space and time. We think about space as absolute, that many of us think of space almost like graph paper, and you're at coordinate 0, 0, and here's coordinate 1, 1, and so on. Einstein teaches us that we should think about space differently. In general relativity, space is relative. It's a theory of relativity. We specify the structure of space by specifying the distances between objects. So if I were to tell you the distance between New York and Madrid, Madrid and Moscow, Moscow and Tokyo, Tokyo and San Francisco and New York, that's enough information for you to figure out that the Earth is curved, because you're able to eventually come back. So you don't need absolute distances, you just need relative distances. That concept's important because when we take our two ingredients for the theory of general relativity, the idea that the distribution of matter tells space how to curve, and the curvature of space tells matter how to move, combine that with the observation that the universe on its largest scales is uniform, that if you look out in space in that direction, and that direction, and that direction, the universe looks about the same on its largest scales, so we know the distribution of matter is uniform. Well, you're now all general relativists. You know the distribution of matter is uniform. You plug that into the equations of general relativity. This part I haven't trained you on yet, but believe me, I'll let you know the answer. The answer is it tells you that the universe is expanding. And the basic solution that relativity tells you is we live in an expanding universe. Now, what do we mean by that? Remember, relativity is about specifying distances. It says the distances between objects are growing with time. That today, it may take 100 million years for light to go from our galaxy to that galaxy over there. If we send that same signal, perhaps 50 million years in the future, since the two galaxies are moving apart, in the future it will take 200 million years. The distances between objects are growing with time. This is counterintuitive, and a question that I often get, a question that I think occurs to many of us when we think about this. If space is expanding, what is it expanding into? Well, it's not expanding into anything in a sense. It's actually expanding into time. The distances themselves between objects grow. That's the weird thing about relativity that you have to accept when you think about the Big Bang model. But it's sort of an inevitable consequence of thinking about the expanding universe. Now, once you realize the universe is expanding, you can then run things back in time. I actually prefer the name expanding universe model to the Big Bang theory for our theory of cosmology. Because what the key concept in the model is the universe is expanding. It is getting less dense with time, and as it expands, it gets colder. Given that it's expanding, we can go back in time and say, well, what did the universe look like in the past? Well, roughly 7 billion years ago, the universe was about half its present size. The distances objects were closer. The density was higher. The temperature was higher. The further back you go in time, the denser and hotter the universe gets. When the universe was 1/10 its present size, the temperature was 10 times higher. And going further back, the temperature just continues to grow with time. So that's the basics of the Big Bang theory. The other important piece you need to think about with the Big Bang theory is something we call the cosmic background radiation. This is the leftover heat from the Big Bang. This leftover heat today is at 3 degrees above absolute zero. For those of you in a very cold place at night, you might find it slightly reassuring that no matter how cold it gets in the universe, you'll never get below 3 degrees above absolute zero unless you're inside a freezer, because space itself is just filled with heat. Those of you who had televisions in the time before cable TV, do people have cable TV here? Yes. So if you remember the old TV with the antennas, there used to be a lot of static when you turned between channels. About 2% of the static when you switch between channels on your TV is microwave background radiation. So probably all of you switching between channels have seen the leftover heat from the Big Bang. If you had done that prior to 1965 and designed an experiment that showed that was from the Big Bang, you would have won the Nobel Prize. So it's a missed opportunity for most of us. I was only 4 at the time, so my chances were low. But this is what Penzias and Wilson did, working at Bell Laboratories, studying the sky in the microwave. They looked out in all different directions and saw this leftover microwave background radiation. That radiation today is at 3 degrees above absolute zero. As you go back in time, it gets hotter and hotter. So now let's run our clock back in time. Today, the universe is at 3 degrees above absolute zero. We go back here to when the universe was 1,100 times smaller. That's what we denote with redshift. At that time, the temperature was about 3,000 degrees. Above that temperature, all of the hydrogen in the universe was ionized into electrons and protons. Before this moment, there's a dense fog, and you can't see back before this time. So when we look out at the universe, we look back in time to this moment when this dense fog formed, and we are seeing the universe 400,000 years after the Big Bang and seeing how it evolves. And the story I'll talk about tonight is how we use our observations of what the universe looked like then, 400,000 years after the Big Bang, to learn both about what happened before the first moments of the universe, looking back to a moment we call inflation, when we think the universe expanded very rapidly. Also use our picture to go forward in time, to take our initial conditions and see how from these early fluctuations, galaxies, clusters, large-scale structure, planets, and even life itself emerged out of these initial conditions. To focus in detail on what we're looking at, we need to keep track of the fact that how the density evolves as the universe expands. On the x-axis is the size of the universe, where when we say 1,000 here, which is the redshift, we mean things are 1,000 times smaller, 10,000 times smaller. As the universe expands, so time is going in this direction, the density of matter and radiation drop with time. As that density drops and the temperature drops, the universe makes its transition from being ionized to being neutral. And when I show you pictures of what the universe looked like when we look out in the microwave sky, we're basically getting a snapshot of what the universe looks like at that moment of transition from being ionized protons and electrons to neutral hydrogen. Now, when I show you these pictures, you should keep in mind that we're looking at radio wavelengths, not optical wavelengths. Most of what we see when we see astronomical instruments comes from telescopes like these. These are very powerful telescopes. They give us an important part of the story, but they don't tell us about the microwave background. To study the microwave background, we need radio telescopes. Oops, there they are. And we'll talk tonight about radio telescopes like these. Here is the WMAP satellite at the top. That's the one that focused primarily on. Here's the Planck satellite operating today. And here's a satellite in the ground, the Atacama Cosmology telescope, located in the Atacama Desert in Chile, that I'll talk about towards the end of my talk. Now, when we look out at microwave frequencies and look at the microwave sky, what we see is shown primarily in the top plot. What we see when we look out the microwave sky, if you had eyes that didn't see optical light but radio light, or if you were Penzias and Wilson pointing your telescope, you would see the same radiation in that direction as you do in that direction and that direction. The temperature is nearly perfectly uniform as you look out in different directions. That's because the universe is nearly perfectly uniform. Remember, that's one of the observations we began with when we constructed our Big Bang theory. If you look more carefully, and it took another, about 10, 12 years before people were able to look and see the second picture, you'll see tiny variations at the level of 1 part in 1,000 due to the Earth's motion. This is due to what we call the Doppler effect. This is an effect that's familiar to those of you who sat at a rural train station and watched a train whiz by quickly going to the city as you're a local stop and that train's the express. And you hear the train's whistle. When it's coming towards you, it's a high frequency whistle. When it's going away from you, it's a lower frequency whistle. Something moving towards you looks higher frequency or hotter. Something moving away from you is lower frequency or colder. And that's what it produces this effect in the middle picture. The Earth is moving towards that red hot spot. Red is hot in this plot, blue is cold. Because of the Earth's motion relative to the average distribution of matter in the visible universe, we get a hot spot in that direction, a cold spot in the other. This effect is of order 3,000th of a degree, 3 millikelvin. It's a very small effect compared to the uniform temperature. If we remove that effect and look even more carefully, at the level of 1 part in 100,000, we get this picture shown below, which is the image that the COBE satellite took of the microwave sky when it made the first detections of the microwave background fluctuations. And what you see here are tiny variations at the level of a few millionths of a degree, microkelvin. And these tiny variations reflect variations in density of the universe back 400,000 years after the Big Bang. Now, the confusing thing in this picture is the stuff on the bottom and the top of this lower picture is the microwave sky. The stuff in the center is our own galaxy. We live in the middle of the Milky Way galaxy. There's dust in the Milky Way galaxy emitting radiation at these frequencies. There are electrons in the in our galaxy moving around emitting radiation at these frequencies. And this dust and electrons are a source of what we call foreground. So this big red thing across the center of our picture, and we've chosen our coordinates so that the Milky Way sits in the center, is our own galaxy. I have friends who study the galaxy. They're interested in that part of the picture. But as a cosmologist, I'm interested in this part below and above, where we're seeing things, fluctuations that were produced in this very early universe. What we wanted to do was study these fluctuations in more detail. So Kobe gave us that broad brush picture, and we felt we could learn more by getting a more detailed picture. What we did was we proposed to NASA to build a new satellite. What NASA does, and the European Space Agency does something broadly similar, slightly different in how they operate this, is every few years NASA announces they want to build a new satellite to do something interesting in astronomy. Tell us what's the most interesting idea you have. They don't specify at all what the satellite should do. They just tell you, in our case, how much money you have and what launch vehicle you go on, and you send in a proposal. So when we did this, 45 groups sent in proposals. After all, it's a very exciting opportunity to have NASA launch your idea into space. Of those 45 groups, they selected 8 of us for more detailed study, and we were one of those 8. And then we spent a year or so writing a detailed proposal describing how the satellite would work, sent it into NASA in 1994. We were selected in 1995, started building it in early 96. And in 2001, the satellite went up in space. Here's our satellite on top of a Delta rocket. This was, for me, one of the most exciting moments, to be at Cape, watching a satellite you work on go up in space. It was very nerve-wracking also, because you knew if the rocket blew up, that was it. My own role in this experiment is I'm a theorist, not an instrument builder. I was involved in the design, but didn't actually build it. My role was mostly in the analysis. I like to compare this. I'm a father of 3 children to my experience of fatherhood. I believe I had something to do with the conception. There was a 9-month period of gestation where, to be honest, I didn't do anything important. My wife did everything important, and I just said, it's going to be wonderful when the child was born, and tried to say supportive things. And then there's a very exciting moment of birth, followed by several years of sleepless nights when we both took care of the babies. This is what it was like to be part of the satellite. It was this very exciting moment of launch. Then we started to get the data, and then all of us involved had many long, sleepless, and exciting nights analyzing the data. I also had the 3rd child at that time, so I don't quite know how I did it. It's all kind of vague looking back on it 10 years ago. Well, once we got the data, we took images of the sky. And these are images of the microwave sky. And we took these images at 5 different frequencies. And the reason we did that was so that we could understand the contribution of the galaxy. So this is the image at our lowest frequency, 22 gigahertz. And at this lowest frequency, emission from the galaxy, this bright red part here, is dominant. And you can see the galaxy is quite bright. As we go up in frequency, the galaxy gets dimmer. And this is still higher frequency. You notice the galaxy becomes less and less prominent. And we can focus on the upper and lower parts, the upper and lower hemispheres. Keep in mind, we're looking at a sphere here around us. So we can look at the northern and southern galactic spheres, avoid the galactic equator, and you can see that we're really dominated by microwave fluctuations. And the fact that they're thermal, basically they look the same at these 2 frequencies, you notice the picture changes very little, tells us that we're seeing thermal fluctuations from the early universe. We could zoom in on these patterns of hot and cold spots and we see many hot and cold spots. We see about 40,000 of them. And because of that, we can measure their size quite accurately. What we do is we combine all our frequencies to make a clean map. We've combined them in such a way that we remove the galaxy as best we can. If you look quite carefully, you'll notice right around the equator, the picture does not look quite even. And that's because we've not removed the galaxy perfectly. We do the best we can. And this represents, at the moment, our best picture of what the early universe looked like. I should note, and I'll come to this at the end of my talk, we actually have a better picture than this, taken by the Planck satellite. The Planck satellite was launched a couple years ago. It's not reporting its first results till 2013, roughly 10 years after WMAP. So there are better pictures than this, but no one's allowed to show them to you yet because the science teams are still working on them. Since I'm not part of the Planck science team, I'm not at risk of showing you results that I don't have. But this represents, as of today, in terms of what we can show, our best image of the early universe. Now, what you're seeing here is just a pattern of hot and cold spots. You're seeing tiny variations in temperature. This hot spot might be 100,000th of a degree, 0.00001, if I counted right, degrees warmer than this cold spot here. So we're seeing very tiny variations from place to place. These tiny variations represent variations in density of the universe from place to place. This region is denser than that region. What we do to study this picture is look at its statistical properties and measure what is the amplitude of fluctuations as a function of scale. We basically throw down circles, average the temperature in circles, and look at the average amplitude of fluctuations versus scale. There are some funny features in the map. People write about them all the time. My favorite funny feature was one that I noticed with my colleague Lyman Page when we were sitting at a meeting about 6 months after this data first came out. During this talk, a guy named Stephen Hawking, you may have heard of him, was giving a talk about our results. And he had this figure behind him without the big circle. And Lyman turned to me and said, his students have put the letters SH in our map as a joke. It's coming. You'll see it. But we then opened our laptops, since we had all the data on our laptops, looked in our data and realized they didn't do it. Nature comes with the letters SH written on the sky. And I have many theories for the origin of this letter. It could be a message about Stephen Hawking. In 2003, this was right before the United States invaded Iraq. I thought it was a message about Saddam Hussein. But finally, for those of you who are familiar with English, I thought maybe we didn't do a very good job removing all the foregrounds, and we're missing 2 letters, the I and T. But most likely, it represents the fact that our eyes are good at finding patterns, and that we evolved to basically be able to see the tiger in the woods and jump whether or not it was a real tiger. And when we look at this map, many people find interesting patterns, but most of our analyses basically show that the whole pattern we see here is basically what we call random. There's no statistical correlations beyond the pattern of what the amplitude of hot and cold spots are. And the fluctuations are what we call Gaussian. So the amplitude is drawn from what's called the bell curve. There's equal number of hot spots and cold spots, and no spot on the map that's particularly extremely hot or extremely cold. Because of that, the statistical properties of this map can be described entirely by a function that we call the power spectrum. And I'll focus on this plot here. And this shows the amplitude of our temperature fluctuations. This thing we plot here is just saying what the temperature fluctuations are in millions of degrees versus angle on the sky. The points are our measurements. We take this data and measure this lumpiness versus scale. The black points come from the WMAP experiment, and the points here come from measurements on the ground. This plot here represents the state of our knowledge 3 years ago. Later in the talk, I'll show you progress till today, and you'll see the plots improve dramatically. But already, this is pretty impressive. The points are our observations. The red curve is our theory. And if we take our simple model, the simple model has basically 5 parameters to describe the temperature fluctuations: how old the universe is, how many atoms there are in the universe, how much matter there is in the universe, the lumpiness of the universe, and how that lumpiness varies with scale. Those 5 numbers. And with those 5 numbers, we predict this curve. We add a 6th number, which describes the pattern of polarization and tells us where the first stars form. And we can completely describe our data. And this is a very simple model. This data tells us a lot about the basic properties of the universe. For example, it tells us the geometry of the universe. Remember that we talked about early on that general relativity says the Earth could be, distant things could be flat, they could be curved like the Earth. So we could measure the geometry of the universe and see whether it's flat, positively curved like the Earth, closed, or negatively curved, what we call an open geometry, like that. If the universe was flat, the pattern would look like this. Positively curved or closed like this, negatively curved like that. So by seeing how big the spots are, we can measure the geometry of the universe. When we look at our data, measure the spot size, this position where the amplitude of fluctuations is largest, roughly 1 degree on the sky, corresponds to the flat case. This means the universe is described by the simplest possible geometry. That the geometry that you learned when you were probably 13 or 14 years old, the Pythagorean theorem, the sum of the sides of a triangle is 180 degrees. This may be familiar thinking back on our youth. That geometry is valid not only on a piece of paper, not only in your school exam, it's valid on the size of the visible universe. That the sum of you draw a triangle connecting 3 distant galaxies, the sum of the angles of a triangle is 180 degrees. Right? That's not true on the surface of the Earth. You draw a triangle connecting New York, Madrid, Tokyo, back to New York. The angles don't add up to 180 because the Earth is curved. So the geometry of the Earth, of our universe, is flat. This has very interesting implications for the physics of the universe. You're all general relativists. We all are now. As general relativists, you know there's a relationship between curvature of space and the amount of matter. That relationship says to have a universe that's flat, the total energy of the universe must be 0. That implies that the energy in expansion, matter moving apart is positive energy, is exactly balanced by the gravitational energy of the universe. Intriguingly, this is just what was predicted by models of the early universe theories like inflation. So based on this, we now have a simple cosmology that fits all the data. This simple model with only 5 parameters. One of them is the age of the universe, which we've measured quite accurately. But as I mentioned in the beginning of my talk, this model is both simple and strange. Atoms, the stuff that makes up us, makes up only about 4% of the universe. The next, 23% or so, is made up of what we call dark matter. These are particles that, like ordinary atoms, feel gravity, but have very weak interactions with light, with protons, with electrons. We don't know what the dark matter is. We can weigh it. We know pretty accurately how much stuff there is in the universe as a whole. We've actually had evidence for this dark matter in various ways going back 60 years, almost 70 years. And this dark matter seems to fill most galaxies. Our galaxy is 70% dark, no, maybe 80% dark matter. What's even stranger is there is energy associated with empty space that doesn't gravitate. This energy is what we call dark energy, and it makes up about 73% of the universe. The other thing that we've observed, and I've mentioned this in the beginning of my talk, beginning of the discussion of the microwave background, is the fluctuations we see have a pattern that we call scale invariant. The amplitude's about the same on all scales, and they have the right properties to see the formation of the galaxies. This last statement, together with the geometry, is very consistent with a very attractive idea for what happened in the first moments of the universe, a theory called inflation, that implied during the first moments after the Big Bang, the universe underwent a very rapid period of expansion. It's an idea that back when I was a student seemed very attractive but very speculative. And it's really remarkable that we are now able to test ideas about the first moments of the universe through observations of the microwave sky. So this notion that to me is so surprising is the universe is very simple. When we look at our data, we don't see any real evidence for anything unusual. So this plot, which I'm sorry didn't come out so well, I didn't transfer the colors well here, is the number of hot and cold spots versus amplitude measured on different scales. And what you should see is the red curve is a Gaussian distribution, this bell curve. The black points are the data. This is measured on the 4-degree, 1-degree, and quarter-degree scale. This says there are equal numbers of hot and cold spots, and their amplitude on any scale is described by one number. So this is a really simple universe. We take these temperature measurements, that map I showed you, we measure numbers, we measure 1 million numbers. We measure the temperature at 1 million points on the sky. All of that information about those 1 million points, statistically, seems to be encoded in a handful of numbers. We see no evidence for variations in the properties of the universe. The fluctuations that we study over there and the fluctuations we study over there all have the same properties. It's the same, they're very far apart, they're billions of light years apart, yet the universe looks the same. We see no evidence for what we call global topology. One of the questions that I've thought a lot about is the universe finite or infinite? And can we see evidence that the universe is finite? A finite universe is one like the surface of, say, a donut. You go around it once, and you come back to where you started. If this room was all there was to the universe, if I left through that door, I would emerge immediately there. that's a finite universe. And it could be the universe was finite. If it was, we would have seen the same pattern of temperature fluctuations over there as we do over there. We look for this. It's a very distinctive pattern. I could actually tell you a funny story about this. So the pattern that's predicted if the universe was finite is we would look at a circle over there and see the same pattern on the sky that we do over there. So to look for that, we took the data, took this map, and drew many circles, one over here and one over there and one over there, and compared all the possible circles. If you think about the number of circles that you can draw on a picture like that, you need a supercomputer to look for all the circles. If you're going to write a computer code for looking for things on a supercomputer, the way you write a computer code to do this is you first write a code to generate a simulated sky that looks like it should look in a finite universe. So you can test and show that your code works. That's really essential for anyone who does scientific programming. You need test code. So I had test maps, and I tested the code on the test maps, and it worked. And then it was time to check it on the test data. But remember, I'm up all night either working on the data or taking care of a 6-month-old. I looked at the data and found that the universe appeared to be finite, and there were patterns of matched circles. It's about 3 in the morning. I was pretty excited. Went back to bed, couldn't really sleep. At 7, my wife got up. She's a medical doctor, but she knows what I work on. I told her, I think I found the universe is finite. Got pretty excited. I emailed my colleagues working on the satellite data, told them what I thought I found. About 5 hours later, my colleague Gary Hinshaw wrote to me and said, what data are you using? He wants to test the pattern to make sure he sees the same thing using some code he has. And I look at the file, and it's called SkyMap. So, okay. Then I look at the test data file and realize late at night, I wrote the test file with a simulated sky on top of the real data. And yes, there is just the pattern that the simulations predict, but that's because, well, this is the real data, believe me. I didn't overwrite the only copy. I was looking at the simulations. So for about 20 hours, I thought I proved the universe was finite. It was a very exciting 20 hours. A little disappointment, I must admit, when I realized what I had done, but much better that I discovered this within 20 hours than issued a major press release about the discovery. I think many people in science have had this experience one way or another where you think you've done something truly awe-inspiring. It all seems to work. This was one of my moments. But the universe turns out not to have these patterns. Maybe it has that one. So as far as we can tell, the universe has no evidence for global topology, or equivalently, the universe is really big. If you keep going for 30 billion light years in that direction, you're not going to come back there. I can't promise that if you went for 100 billion light years, you won't come back, because we can only see so far. But as far as we can tell, we live in a big, flat universe. That's one of the things we've learned, and a universe, to keep coming back to this theme, that is remarkably simple. So now we've taken the universe's baby picture. And these are 3, let's say, randomly selected children when they were 3 days old. If you know the initial conditions, and children were as simple as the universe, which they're not, you can run them forward in time. Oh, and this is what they look like about 6 years ago. So that's looking back to redshift 1. And you study the properties then. And here they are. This works. Oh, there we go. Well, believe me, you don't really need pictures of my kids, but they'll quickly flash by. There it went. That was them 2 years ago. We do the same thing in cosmology. We take our initial conditions, we take the patterns we see in the microwave sky, put them into a computer simulation, start with, as this simulation does, a nearly uniform universe, and then show how from tiny fluctuations in that nearly uniform universe, galaxies and clusters can form. And we'll just keep running this over and over again, and you'll see how gravity transforms small variations, these variations of 1 part in 10,000 of the density of the universe, to rich structures as we go from the moments, the picture we see in WMAP to today, and we can compare these statistical properties of the patterns we predict in our simulations to the observations and tests our idea of the universe. And what you see running down here in this clock is the redshift of the universe. So redshift 0 is today. So let's compare the universe that we predict from the simulations, predict from our data from WMAP, looking at the early universe, to our observations of the universe today. We do this primarily using data from the Sloan Digital Sky Survey. This is a survey of the galaxies in the northern sky. This survey has surveyed over 1 million galaxies in the nearby universe and measured its positions, got images of over 100 million galaxies. This survey, when we did it a decade ago, was by far the largest project of its type. Today, it has spawned many successors. There are projects like the Dark Energy Survey that people here in Spain are part of that are follow-ups on surveys like this, except for they will go much deeper and much further. But this represents where we are today with the data, and this is a measurement of the amplitude of fluctuations, how lumpy they are versus scale. This is an analysis done by my student Beth Reed, which work she did when she was a postdoc here in Spain in Barcelona, working with my colleague Alicia Verde, who had twins yesterday. We just got very nice pictures. Amusing to me, but irrelevant for the talk. And what Beth did was she took the data collected from the Sloan survey, measured the amplitude versus scale. This black curve with no free parameters, we take what we see in the WMAP sky, we run it forward in time, we predict that the galaxy data should follow this black curve. The points are the black curve. I find this startling. This implies we can take observations we make of the very early universe, use that as initial conditions, and understand the large-scale distributions of galaxies today. It implies we have a coherent model that fits observations across 13.7 billion years, and a model described by basically only 5 parameters. Nothing else is needed. In fact, when we look at all of our data, all the pieces fit together. This plot below shows the brightness of supernova versus distance. The data from the supernova surveys are shown in these points here. This is a French survey led by the Supernova Legacy Survey. Here's a survey combining a bunch of data sets led by Adam Rees. If the universe did not have this dark energy in it, it would basically follow a line like this dashed line. Based on the WMAP data, the best fit is this black curve, and you see it's very consistent with the supernova. The supernova data was earlier than our data. The supernova data was taken primarily in 97 and 98. And it is the supernova data that showed evidence for the accelerating universe. Our friends in Stockholm were pretty excited by the supernova data, and I like to think convinced by our confirmation of it. And this year they granted the Nobel Prize in Physics to Adam Rees, Brian Schmidt, and Sol Perlmutter for their very important work beginning this program of successfully using supernova to measure the acceleration of the universe. So that's a very important confirmation, a very important piece of this overall model. Other pieces are measurements of the Hubble constant by the Hubble telescope. And this, to give you a sense of where we are in cosmology, right now, based on the WMAP data, we measure that the acceleration, the rate of expansion of the universe in units of kilometers per second per megaparsec, the relevant units. We measure it's 72 with an uncertainty of 2. And people using the Hubble telescope measure it very differently using the expansion rate of galaxies and find 73 with an uncertainty of 2. So we have this remarkable quantitative agreement between two different techniques on the expansion rate of the universe, the Hubble constant. The measurements of the age of the universe is consistent with the measurements of the earliest stars, measurements of properties of clusters. One of the most compelling measurements are the cosmic abundances of elements like deuterium and helium. Most of the deuterium in the universe is produced in the first 3 minutes of the Big Bang. The amount of deuterium depends upon the density of atoms. So my colleagues studying the amount of deuterium seen towards distant quasars can infer the abundance of atoms in the universe. In fact, David Teitler, my colleague at UC San Diego, who works on these cosmic abundances, back in 2003, when we were doing our analysis, he was doing his work on the deuterium abundance. He knew he wasn't going to publish his results until after ours. So the day before we made our announcement, David emailed me and said, just so that you know we're not changing our results when yours come out, we have measured the deuterium abundance, and we've inferred the universe is 4% hydrogen. We looked at our data. We had already done our analysis. We also found 4% hydrogen. Given the error bars in our results, they agree to better than 10%. So we can look at the abundance of atoms in the universe based on chemistry that happened 3 minutes after the Big Bang. That's the deuterium work. We can look at our measurements of the patterns of hot and cold spots, and we get the same answer. I find this really reassuring. We're building, I think, an intellectual house not on sand, but one that has many cross-checks. Other cross-checks come from measurements of gravitational lensing and studies of fluctuations based on looking at absorption of gas towards distant quasars. These quasar absorption lines tell us how lumpy the universe was when it was a third of its present size. To go back to the pictures of the kids, it's what the universe looked like when they were littler, right? And all the pieces fit together. So today, we now have what I would call a cosmological standard model. As I was stressing, the basic parameters of these models have been determined in many different ways. I have emphasized in my talk today how we measure the parameters from the microwave background data, but there are independent ways of measuring them from the Hubble telescope, from looking at the expansion rate of the universe, from the supernova data, the cosmic abundances, the density of galaxies and how lumpy they are. All these different techniques are giving consistent answers. So if you look at the state of cosmology, the glass is half full version of cosmology is everything fits, we understand what's going on. The glass is half empty version of cosmology is we only know what's 5% of this glass. The remaining 95% is made of stuff that we don't know what it is. And it is difficult to stand in front of you and tell you, I understand the universe, I know what's going on, when we don't know what 95% of it is made of. This makes this a very exciting time to be a cosmologist because we don't understand so much about it, yet in some ways it all seems so simple. Another very interesting part of this story is not only have we learned about the universe of what's happened since 400,000 years after the Big Bang, we've been able to look at the patterns we see and use it to test ideas about the first moments of the Big Bang. The fact that we see the same pattern over there as we do over there, and the fact that the patterns are so simple, is consistent with the idea that early in the universe, it underwent an extremely rapid period of acceleration, much like the acceleration we see today. And this period we call inflation. And when astronomers say inflation, it's not like when bankers talk about inflation. It's not the prices going up. It's the scale of the universe growing rapidly. So, where are we now? We're left with some very interesting questions. What's the dark energy? What is the dark matter? Why is the universe expanding? Why is it accelerating so rapidly? And finally, how did the universe begin? So to address these questions experimentally, we want to continue to improve our microwave background data. That's one piece of how we study this. I've talked about going from COBE, measuring maps on this scale, to WMAP. The next step in terms of measuring the whole sky is the European Space Agency's Planck experiment, an experiment that many people here in Spain are involved with, that is measuring the sky at 3 times the resolution. It's able to see many smaller patterns than we did with WMAP, and 10 times the sensitivity. We do not yet know what Planck is telling us. It's one of the very exciting things about the field. There's new things about to happen very soon. I think of Planck as having fundamentally one of 2 possible results. Either Planck finds that the model that fits the WMAP data continues to fit. This simple model works, in which case Planck will measure the basic parameters that we've measured to even higher accuracy. Or, what would be even more exciting, is if Planck sees evidence for new physics. And we'll see. Can't talk to you about Planck results, but I can describe some of the work that we're doing looking at even finer resolution. Not at the whole sky, but a small portion of it. So what we're doing is we have a telescope in Chile, in the Atacama Desert, up here, near the border with Bolivia and Argentina, way up here at 5,300 meters. And here's the telescope being constructed. and here's the telescope surrounded by a ground screen. To give you a sense of scale, this is 6 meters, right? Well, from there to there is 6 meters. So this is a big international collaboration, about 80 scientists in 5 continents. We're up here in the Atacama Desert with a 6-meter telescope operating at 3 different frequencies. The best way to actually see the satellite telescope is to go to Google Sky. It's remarkable. If you go to Google Sky and type in your address, you could see quite a detailed picture of your house. It's a little, or apartment. It's a little disturbing, I find. But it's all available on the web. If you type in the coordinates of the telescope, here it is. And the nice thing about Google Sky is you can see the telescope from above. And there it is, looking out at the sky, and here's our roads, and you can see why we go to the Atacama. It is remarkably dry. It is a truly incredible place. When I was there visiting the telescope site, we went to a restaurant nearby, and the restaurant doesn't have a roof because it never rains. I asked the waitress if she ever saw rain. She said yes. She went to Santiago for her cousin's wedding, and that was the only time she's ever seen rain. So this is a truly remarkable place on the planet. It's like being on another planet almost. So what do we do with this experiment? We take, here's our WMAP image, and we zoom in at high resolution to see a small portion of the sky and see the details, and study whether what we see in detail is consistent with this larger picture. This is real data. This is what we actually measure. This is a map of about 5 degrees across. This plot shows about 3% of our data. And what I like about this picture is it shows you a bit of the dirtiness of reality. So you'll notice at the bottom, there are these stripes. See these stripes? That's because the satellite, the telescope, swings back and forth across the sky. And when it gets near the edges, it generates stripes in the map. So we can't use this bottom and top part of the map, which the telescope, as it goes back and forth, spends most of the time in the middle. So we use this data here. You can see these bright spots, and I'll zoom in on them soon. Those bright spots are individual galaxies, are clusters, are radio sources. These are quasars and galaxies, which produce hot spots on the sky. And then you'll notice, if you look carefully, some black dots. There's one, there's another, there's another. They're tiny black dots on the map. Those are clusters of galaxies. There's an interesting effect that's called the Sunyaev-Seldovich effect, after Sunyaev and Seldovich, that arises because clusters produce shadows against the microwave sky. Remember, the microwave photons are traveling for 13.7 billion years from the early universe to our telescope. If they pass through a cluster of galaxies, they will scatter off of the electrons in that cluster and gain energy and scatter out of the frequencies where this telescope is looking. As a result, we'll see a shadow or cold spots wherever the clusters are. So one of the things we'll do, and I'll show you some pictures in a moment, is we go look at our maps, find these cold spots, and then look at optical wavelengths. So we take our maps, and you can see this here. We take our original map. We do some computer tricks and filter it to remove the big patterns. and we find the cold spots, which turn out to be clusters, and the hot spots, which turn out to be galaxies. When we look more carefully at where the galaxies are, this is what we see in two of our frequencies. And here's a picture of galaxy NGC 1055 in the Sloan optical data. And you can see we can detect the radiation from the dust from that galaxy. Do you remember I showed you the picture of WMAP? We saw the dust from our own galaxy polluting our data. Here's the dust coming from a distant galaxy. Same physics. And we see lots of distant galaxies. More interestingly, we see lots of clusters. And this is the biggest cluster we've seen. In fact, the biggest cluster ever detected at microwave frequencies. And we think it's the biggest cluster in the visible universe. Based on that, we've given it the name El Gordo. And here's El Gordo casting a shadow at microwave frequencies. Here's when we look with an optical telescope, we go to Chile and take an image of the cluster. We see a distant cluster here. And here's what it looks like in X-rays. And when we look in detail, this is a very interesting cluster. If you look at the galaxy distribution, there's one cluster of galaxies here and another cluster of galaxies here. That's what it looks like in the infrared. You can see again a cluster up top and another cluster down here. We think we're seeing two clusters merging together. And when that merger takes place, the second cluster, here's a peaks in star counts. We think we're seeing the effects of the mass in the cluster distorting the images of the background galaxy. That's what's called an arc. We're actually seeing the background galaxy distorted by the mass here. And when we look in X-rays, you'll notice the peak in X-rays is around one galaxy, not around the other, one group of galaxies. We think one cluster is ripping through another like a bullet, shocking the gas around it, and we're seeing the interactions between the two systems. So this tells us nothing directly about the early universe, but it's a fascinating system for learning about how structures form and evolve. And this system is, I think, a good example of one astronomer's ugly foreground, these white and black spots you saw in that earlier map that those of us interested in the early universe want to throw out. For some of our other colleagues, is a fascinating system to study to learn about how galaxies form and evolve. And here's some records of this object. We think it's the brightest, hottest, most massive object so far discovered in the visible universe. So, a fun thing to stumble across as your junk. But wearing my early universe cosmology hat today, what's exciting about that data is I can now look for the pattern of fluctuations that we see and look how well it compares to our theory. This is the plot you saw before. We measured the amplitude versus scale, and we saw those three bumps in the data, and we said, I was pretty excited that our simple model fit the data and the pieces held together. These points here in blue represent our measurements in Chile. We see not just these three bumps, we now see bump 4, 5, 6, 7. If you're an optimist, bump 8, and maybe bump 9. This red curve is the theory fit to the WMAP data. So we have no additional parameters, and we're predicting the pattern of fluctuations on much smaller scales. The red points are work done by our colleagues and competitors at University of Chicago, working at the South Pole, mapping the sky with the South Pole telescope. A very comparable experiment in most ways, completely independent analysis, and you could see they see the same pattern. Planck will soon measure this with much higher precision, because instead of looking at what's showed here, which is about 2,000 square degrees in the sky, we'll see it more like 30,000 with Planck. Another effect that we've seen in the microwave sky is gravitational lensing. The fluctuations, the density of matter between the early universe and us deflect the photon's path. To go back to an earlier theme, you're all general relativists. You know that the variations in matter curve space. That curvature of space deflects photon paths. So the microwave photons traveling that 13.7 billion years are deflected as they travel to us. And with our small-scale measurements, we could see this pattern of fluctuations. These ACT results, while very exciting, I think are only appetizers for what we should expect soon from the Planck experiment, which will be mapping the whole sky with the same noise level that we've achieved on small portions of it. And we're all looking forward to see what Planck finds. So let me conclude. I hope you've come away from this talk that cosmology truly is in a golden age, that we have had a wealth of new data coming from many different kinds of measurements, and these observations are giving us a very intriguing picture for the early universe and the properties of the universe today. We seem to live in a universe that is both remarkably simple and remarkably strange. And as our technology continues to advance, as we do new experiments, we are probing deeper into the physics of the universe. This model we have has held together quite nicely for a decade or so, but the data is improving, and we'll soon see if we have had the good fortune to live at the moment in which our basic picture of cosmology gels, or whether this is just a temporary picture consistent with our current data, and as new data comes in, a more complete picture will emerge, and conversations about things like dark energy and dark matter will seem to 22nd century astronomers much like our view of 19th century physicists talking about the ether, or 15th century astronomers talking about stars moving on epicycles, planets moving on epicycles in deference as they consider the orbits of Jupiter around the Earth in their Earth-centered universe. So I hope you've enjoyed this tour of cosmology, and want to thank the Foundation for the opportunity to come here to Madrid to speak to you about this exciting field. Thank you.